Electricity can move through many paths, but what if we want current to prefer one direction and resist the other? A tiny component inside almost every electronic device does exactly that. It's called a diode. Diodes are among the most common electronic components ever created. They exist inside phones, computers, televisions, power supplies, solar panels, and countless other systems. Their job seems simple at first. They allow for electric current to move much more easily in one direction, while strongly resisting movement in the opposite direction. This simple behavior becomes extremely useful in electronics. Imagine a pipe carrying water. Now place a special valve inside that pipe. Water moving forward pushes the valve open and continues flowing. Water moving backward pushes against the valve and encounters resistance instead. A diode behaves in a similar way. Instead of controlling water flow, it controls how electric charge moves through an electrical circuit. To understand why a diode behaves this way, we need to look inside it. Most diodes are built using silicon, a semiconductor material. Semiconductors are unusual because their electrical behavior can be carefully changed and controlled. Small modifications to their internal structure can dramatically change how easily electric charges move through the material. One side of the diode is called p-type material. Scientists created by adding tiny amounts of specific atoms into silicon. This process leaves behind many empty locations where electrons could exist. These empty locations are called holes. Holes are not real particles, but they behave as if positive charge can move through the material as nearby electrons shift position. The other side becomes n-type material. Different atoms are added into silicon, so extra electrons become available inside the crystal. Unlike holes, there are real particles carrying negative charge. These additional electrons can move freely through the material. One side of the diode now contains many holes, while the other side contains many mobile electrons. Now bring these two materials together. Electrons on the n-type side immediately begin moving toward nearby holes on the p-type side. As electrons move into these holes, many of them pair up and disappear from the flow through a process called recombination. This movement does not continue forever, because something important begins forming near the center. Near the boundary, an almost empty region begins appearing. Since many mobile charges have already moved away or recombined, very few remain there. This area becomes known as the depletion region. Think of it as a barrier separating both sides. Charges approaching this region suddenly find it much more difficult to continue moving across the junction. Now connect a battery across the diode. The positive terminal connects to the p-type side, while the negative terminal connects to the n-type side. This arrangement is known as forward bias. The battery pushes charges towards the center of the diode and begins reducing the effect of the depletion region barrier between both sides. As the barrier becomes smaller, charges can move across the junction much more easily. Electrons begin crossing the diode and a steady flow of current starts moving through the circuit. The pathway has not become perfect, but moving through it suddenly becomes much easier than before. A much larger current can now flow through the device. Now reverse the battery connections. Positive connects to the n-type side and negative connects to the p-type side. Instead of pushing charges towards the center, the battery now pulls them farther away from the junction. Rather than reducing the depletion region, the battery causes the barrier inside the diode to become larger. As the barrier grows wider, crossing it becomes much harder for charges. Under normal conditions, only a few small amount of current remains, often limited to a tiny leakage current. The diode now strongly resists the movement of current. This behavior is what allows the diode to control the direction in which the electrical energy can easily move. Real diodes have another important characteristic. Current doesn't suddenly appear at one exact voltage value. Instead, current increases gradually. Imagine slowly turning up the voltage across the diode. At first, very little current flows. As voltage rises further, current starts increasing much faster. In many silicon diodes, this becomes noticeable around 0.7 of volt. One important use of diodes involves converting alternating current into direct current. Electricity from wall outlets repeatedly changes direction many times every second. However, many electronic devices work better when current mainly moves in one direction. Diodes help remove part of this back and forth motion and assist in creating a more useful electrical output. Some diodes can do something beyond controlling current. Light-emitting diodes, usually called LED, release energy in the form of light when charge moves through them. Inside the semiconductor, energy changes create particles of light called photons. This same process powers indicators lights, displays, flashlights, television screens, and modern lighting systems. Engineers created many specialized versions of diodes for different tasks. Some help protect circuits from sudden voltage spikes. Others detect radio signals or regulate voltage levels. Certain diodes are even used to create laser lights for communication systems and technology. Although their purpose differ, they all rely on controlling electrical current. Modern technology depends heavily on diodes, even though most people never notice them. These tiny components quietly guide electricity through billions of circuits every second. They help protect devices, convert power, produce light, and improve reliability. Many technologies that people use every day become much more difficult to build without them. A diode may appear small and simple from the outside, but inside it, a complex process controls how electric charge moves. By making current travel much more easily in one direction than the other, diodes became one of the foundations of modern electronics. From tiny devices to large systems, they quietly help power the technology around us.